I want to show you today what it means to complete the square. So you might have been asked before to solve something by completing the square and being completely thrown off. Well, let's investigate a little bit. Our quadratic equation is normally in the form x squared plus bx plus c. Just note that I have no equation or a coefficient here for x. That's going to be important later. So, if I rearrange this, I can say x squared plus bx is equal to minus c. Okay. Now what this means effectively, if we look at our area models that we've been looking at, that we've been investigating quite a lot in the past, is if you were to draw this as an area, we could either draw this as x squared, okay, so there's a square, that's x squared, and then we could say bx, but now we've deliberately chosen to do a half of b by x on this side, no half of b on x and x on this side. Now the reason we've done this is because we've got a tiny little square at the bottom here, which is actually a half of b squared as its area. Now why this is important is that in this form you cannot isolate x, but maybe if instead you think about it as an area, and on this side you have x plus a half b times x plus a half b, that's x plus a half b squared, is the same as the area minus this little square that we did not include. So, if I square this whole thing, that squared, we'll get an area plus a little bit. So, that should be equal to an area, same area that we had, minus c, and a tiny little green bit, half b squared. So effectively what I can do now is I could square root both sides and I will only have one instance of x. So if I square root both sides, I'll have x plus half b is equal to an area, that's minus c plus half b squared, or square rooted. And then I can isolate x. X is equal to the square root minus c plus half b squared minus half of b. So I've managed to isolate x from a quadratic form using just a rectangle. So how can I apply this theory to this problem over here? Well, let's give ourselves some space. I'm going to just get us a line in the middle here. Okay, so the first thing we did was we made it in the form x squared plus bx is equal to an area. Okay, so let's do that. X squared plus bx is equal to an area. Now, the next thing that we did is we added a tiny little rectangle to turn this side into a complete square. So we said half the coefficient of the middle term, so half of b is the coefficient of the middle term, and we squared it. Okay, half of b squared, that's, we're going to add that to this side, x squared minus 13x plus, we're adding this rectangle, half of the middle term, which is 13, that's half the coefficient of the middle term squared, and on this side minus 45 plus half the coefficient of the middle term squared. Okay, so from here what we can see is we've got a perfect square on this side. Okay, so let's use this perfect square that we got. That's the same as saying x minus 13 over 2 squared. And you can test that if you'd like. Multiply this out and you'll notice that you'll get back to this. And that's equal to, now you can get out your calculator and get the value for that, minus 45 plus 13 over 2 squared. So we can actually go ahead and square root both sides. When we square root this side, and you square root that side, what you do to the one side, you do to the other side. So x minus 13 over 2 is equal to the square root of minus 45 plus 13 over 2 squared plus 13 over 2. And we can type that into our calculator. Sorry, plus 13 over 2, just this 13 over 2. I've added 13 over 2 to both sides. Okay, and there you've got your value for x. Now I'm not going to type this into my calculator, I don't have it handy, fortunately.